the program that you're here for. Today's Alumni College session, Polar Regions and Climate Change, will run for about 85 minutes. Our speaker will present for about 25 minutes, and then we'll have 45 to 60 minutes for Q&A. It's my honor to introduce Dr. Kelly Kennison-Falkner, class of 1983, director of the National Science Foundation, Office of Polar Programs, and the U.S. Antarctic Program. She's the founding program director of the Antarctic Integrated System Science Program at the NSF. Dr. Falkner oversees 65 staff and an annual budget of $500 million, covering scientific research and operations in both the Arctic and Antarctic. Prior to federal service, she was a professor in the College of Oceanic and Atmospheric Sciences at Oregon State University, where she taught and conducted research for 26 years. After getting her BA at Reed in chemistry with Russian language studies, she went on to earn a PhD in chemical oceanography from the Woods Hole Oceanographic Institution, MIT Joint Program in Oceanography. She explored the seas and ice caps of polar regions for 3 decades as an oceanographer, seeing firsthand through her research the dramatic changes in the Arctic and Antarctic resulting from climate change. Now I'm going to turn it over to Dr. Falkner. Thank you for being here.
Good morning, everyone. Thank you for taking time out of a Saturday morning to be here to share this experience. So I'm really pleased to be here because I understand that this is the 10th anniversary of the inception of the environmental studies concentration at Reed. I likely would have been an environmental studies major had there been such a possibility. I think, it's good on Reed for finding its way toward encouraging robust scholarship in this domain. I can't probably stress enough the need for dedicated critical thinking in among society's greatest challenges, namely climate change and all of its manifestations. So as was mentioned, we'll dive into the role of polar regions and climate change over the next 25 minutes or so. I'm going to start off with a little bit of background regarding my current professional vantage point. And then in the spirit of David Letterman, and by even using that name, I'm probably dating myself, we'll cover the top 10 things I think you should be aware of on this subject. So, and I could see from the sign-up information that you all come from really fascinating and diverse backgrounds and professions, life experience. So I'm really looking forward to hearing your thoughts and questions in this topic after I've finished the initial presentation. So with that, I think we should get going with the slides. Okay, and if you'll go to the next slide, please. All right, so I want to let you know I'm going to stop my video while I'm speaking. I'll come back after I finish presentation because I find that it keeps things stabler on my internet connection. So as noted, I have the pleasure of serving as a director of the Office of Polar Programs at the National Science Foundation. And many of you may be familiar with the National Science Foundation, or NSF, as we say. But I find that even in Washington, where we're headquartered, people aren't quite sure what we do. Some confusion stems from our name, since in common parlance, foundation tends to evoke private entities that exist to raise money for various causes. And also, we are not the nonprofit National Sanitation Foundation, whose stickers you can find all over the place. We are an independent federal agency founded in 1950 by Congress to promote the progress of science, to advance the national health, prosperity, and welfare, and to secure the national defense. So NSF supports basic research and people to create knowledge and build capacity to innovate and lead the world in science. So in 2021, with a budget of $8.5 billion, we are the funding source for approximately 25% of all federally supported basic research conducted by America's colleges and universities. Next slide, please. So the Office of Polar Program promotes the National Science Foundation mission by supporting, as it says here, creative and innovative scientific research, engineering, and education in and about the polar regions. So the OPP research portfolio encompasses fundamental and system level studies across nearly all areas of research supported by NSF. And so to facilitate polar research on behalf of NSF and other communities, OPP exercises operational responsibilities over infrastructure, logistics, health, safety, environmental stewardship, and international collaboration. And as mentioned, I have significant resources to do this, just a bit over $500 million per year, and additional appropriations for major facility construction projects. And of course, I don't do this alone. I have a team. My staff of about 65 are assisted by over 1,000 contracted staff, and then cost reimbursable services from throughout government. So in the Antarctic, OPP executes a presidential memorandum that charges NSF with managing the US Antarctic program on behalf of the nation. And ex officio, I serve as the director of the US Antarctic program. In the case of the Arctic Research Policy Act names the NSF director as chair of the Interagency Arctic Research Policy Committee. And OPP supports the chair role of that committee and promotes active interagency engagement toward a well-coordinated national Arctic research agenda. And through participation in US delegations to the Antarctic Treaty System and in activities related to the Arctic Council, my office supports the nation's polar geopolitical interests. Now, science has long been a fundamental component of international cooperation in the polar regions. The International Geophysical Year in 1957 and 58 led directly to the formation of the Antarctic Treaty in 1959. And Antarctica is the one continent set aside for peaceful scientific purposes. In subsequent years, science supported within the Antarctic Treaty System led to the negotiation of the Convention for the Conservation of Antarctic Marine Living Resources that governs fishing in the Southern Ocean, and the establishment of the largest marine protected area on the planet in the Ross Sea. And similarly, the Arctic Council grew directly out of cooperation fostered by International Arctic Science Committee, which was guided by NSF leadership. Next slide, please. So with that background, I would like now to share what the top 10 things I think that you really need to know about climate change in polar regions. They're sort of enumerated on the right side of the slide there. And no doubt you've been exposed to at least snippets by the media regarding dramatic changes underway in polar regions. Current warming of our planet due to greenhouse gas emissions presents intertwined complexities for natural and human systems in polar regions. Furthermore, climate-driven changes in polar regions have significant global implications. So as I march you through these 10 major categories of climate-related polar research concerns on this slide, we'll learn in a sort of general way what they are. We could probably dive in each one of these in much more detail. However, I'm going to restrict myself as to just expose you to them, and then we will have time to discuss as you wish. So what we're looking at here is a picture from New York City's subway system during the 2012 Superstorm Sandy event. And even though the system was shut down and preparations made before the storm, the flooding that transpired was well beyond what was predicted. In fact, there was a 13-foot surge at Battery Park. It took several days of heroic efforts to restore service. Now, for a sense of magnitude of impact, realize that in 2011, about 1.6 billion people rode the subway. And one contributing factor to this event is sea level rise, the polar components of which we'll get to shortly. And as you'll see, an important theme to emerge from what I will share is that Arctic change has been kicked into full gear, whereas the Antarctic, which has the potential to provide a bigger punch, is like a sleeping bear at the moment. It is in fact experiencing change that is simply not quite as evident on the surface. There are reasons for that. So keep in mind that the Arctic is a small ocean surrounded by land, and people have long lived there. The Antarctic is an ice-covered continent surrounded by ocean and has no permanent settlers. So next slide, please. I entitled this All Hands on Deck. And as you'll see in the remaining slides, when it comes to climate change, what happens in polar regions doesn't stay in polar regions. So gone are the days when polar regions could be considered remote and disconnected from the rest of the Earth. And what happens there matters to all people on our planet. Hence, tackling issues surrounding polar region climate change requires an all hands on deck approach. To be very clear, all hands are not currently on deck. So as our society is reckoning with issues of diversity, equity, and inclusion in general, we have to acknowledge that we suffer from a lack of diversity in science. And among the disciplines, earth science is among the least diverse, and the situation is even more pronounced in polar science. So what you're looking at at this slide, in the photo on the left, is a picture of the first women who were allowed to step foot at South Pole Station just over 50 years ago. And yes, allowed is the operative word. It took the persistent efforts of women like these and other pioneering women to pave the way for today, when women have actually occupied all categories of jobs in the polar regions, from pilots to heavy vehicle mechanics, to station managers, to chief scientists. Now, I am the first woman to occupy my position, and I've enjoyed interacting with a number of women counterparts who are also first to their roles in the international context. That said, despite decades of investments to encourage diversity, women still make up only about 25% of the polar science community, and they are predominantly white. So at NSF, we also have a special responsibility to include the perspectives and knowledge systems of Indigenous peoples who have been successfully thriving in the Arctic for millennia. Depicted on the right are high school students from Greenland, Denmark, and the US who are participating in the hands-on capacity building that we co-sponsor in Greenland. The US is an Arctic nation because of Alaska. There are 229 federally recognized tribes in Alaska. That's about 40% of all of US recognized tribes. We encourage and support proposals that entail co-production of knowledge with Alaska residents and Arctic Indigenous peoples whenever appropriate. So ensuring diversity and inclusion is my #1 concern, because we need to tap all available talent to get the best polar research ideas on the table and in practice. And tackling polar climate change is fundamentally a people problem, and inclusion requires culture change, which is not easy to achieve. But fortunately, there's cause for optimism. There is support at the highest levels of government to push out on social equity. It is a pillar of the Biden administration. Addressing the so-called missing millions in science is one of the 3 top priorities of our new NSF director. Next slide, please. So with that, let's turn to the environment. Now, I hope you've heard of the term polar amplification. It refers to the fact that as our planet warms, the rate and magnitude of warming are greatest in the polar regions. This is depicted on the top graphic based on observations as a temperature difference between 2019 and 1960, with the red to brown colors showing the areas of largest annually averaged warming. And as you can see, the warming is most pronounced across the Arctic. Multiple factors contribute to the amplification, including the vertical structure, the temperature in the atmosphere, as well as interactions of sunlight with the ocean and land surfaces. And we'll talk a little bit more about those interactions in a moment. It is unambiguous that polar amplification is occurring. And while we understand enough to predict it, we don't completely understand how all the factors contribute to it. And that remains an active area of research. So for now, if you'll focus on the bottom graph of zonally average temperature changes, you can see that parts of the Arctic have warmed by up to 7 degrees Fahrenheit over this time frame. The Antarctic Peninsula has also warmed by this amount, but it's not readily apparent in a zonal average. The magnitude of change becomes particularly important when it brings about a phase change from ice to water, or when you cross through the freezing point, which we have in many of the areas depicted here. Next slide, please. Okay, so one of the more dramatic phenomena has been the retreat of Arctic sea ice. So on the left side, you are looking at a contrast of sea ice conditions in the Arctic. So it's 1980 on the bottom and 2012 on the top. I hope you recognize Alaska on the lower left of each picture, and Greenland is toward the upper right and is covered in grayish white to signify land ice. Bits of the Canadian archipelago are similarly colored. That is not the ice we're talking about right now. I'm talking about sea ice. So the brightest white colors illustrate sea ice that has persisted over several years, or so-called multi-year ice. It tends to be thicker, on the order of 3 to 4 meters or greater. The remainder of the ice area is seasonal ice that is approximately 1 meter thick at the thickest. So both the area and thickness of sea ice in the Arctic has been steadily declining. And the graph on the right shows the calculated change in ice volume over the period of the satellite record from 1978 on the left to now on the right. So while the ice cover grows and shrinks annually, it has on average been losing about 1,000 cubic kilometers per decade. So to give you a sense of the magnitude of that loss, I did a few calculations, and I can tell you that that rate of loss is equivalent to about 80,000 times Portland's municipal water usage, or about 65 times New York City's usage. It's a big number. Snow-covered ice reflects most incoming sunlight, whereas open water absorbs most of it. So as snow melts on the ice and the ice cover itself melts, more sunlight can go directly into warming the ocean. That stored heat in the ocean makes it harder to reform ice, and so it sets in play a sort of feedback cycle that favors continued ice loss. While the ice still forms seasonally when it is cold and dark, the ice tends to be thinner and more readily melts. And the change in sea ice affects all kinds of things, including conditions for shipping, habitat for ice-affiliated organisms like polar bears and walrus, and lower in the food chain, and the safety of ice for subsistence lifestyles and so forth. And if we have time, I'd love to share with you some personal experience with changing sea ice cover at the North Pole. But for now, however, let's consider the fact that as the ice has retreated from the shores around Alaska, it no longer buffers the land from wave actions from the sea. So if you take the next slide, please. So that brings us to an array of changes affecting the land in the Arctic. First, I should note that about 25% of land in the Northern Hemisphere is covered by permafrost. Permafrost is soil in which the water remains frozen throughout the year. As the temperatures have been rising, permafrost has been thawing. The combination of wave action and thawing permafrost has led to greatly accelerated erosion along Alaska coastlines. You're looking at a picture from the coastal Alaskan town of Shishmaref. So there are approximately 30 villages in Alaska that have been identified that need to be relocated due to such instabilities. People who for millennia relied on storing food in frozen ground can no longer reliably do so. So in addition to the threat of infrastructure instabilities, permafrost thawing exposes carbon that's been accumulated over tens of thousands of years. It is estimated that stores of carbon in the permafrost are approximately equal to all of the carbon currently in our atmosphere. Through microbial action, that carbon can be released as CO2, largely under dry conditions, or methane under wet conditions. Methane is also a greenhouse gas. It's 20 to 80 times more potent than CO2. So as such releases could greatly amplify greenhouse gas warming, it's really important to figure out exactly and how quickly this will happen. Carbon also gets stored under conditions found in the Arctic subsea floor in the form of a type of ice we call clathrates that encage methane. We've documented active release of methane from seafloor clathrates over the shallow Arctic shelves in recent years. So more research is needed to determine the magnitudes and future trajectories of these Arctic carbon sources to our atmosphere. And the other graphic on this slide is showing you the decline in snow cover over the period from 1970 to the present. And much like for sea ice, loss of snow causes less sunlight to be reflected back into space as it is absorbed by the dark land, and this reinforces warming. Next slide, please. Okay, so as the land and the ocean and atmosphere are warming, we're seeing major changes in weather patterns. And until recent decades, lightning was not known to be a significant threat in the Arctic. But recent work has demonstrated that this is no longer true. A study in April showed that lightning strikes in Arctic summer season have increased 300% in the last 11 years. Moreover, lightning strikes have been responsible for setting off tundra fires. The photo on the left is from the massive 2007 Anaktuvuk fire that burned on the North Slope in Alaska for 3 months. Record-breaking heat led to massive fires fueled in part by peat in Russia in 2019 and 2020. These two smolder and release carbon and soot that can land on snow and ice surfaces, lower their reflectivity, and further promote melt. In some instances, so-called zombie fires have persisted under the snow cover only to reemerge the following season. Next slide, please. Okay, and so as the Arctic region warms, overall temperature gradient between the North Pole and the tropics is changing. This affects patterns of atmospheric circulation, in particular of our jet stream, which is responsible for delivering our major weather systems. The jet stream flows eastward in a wavy pattern as our planet spins beneath it. Simple physics would predict that with a lesser temperature gradient, the wave heights would elongate and the wave train would move more slowly. We have in fact been experiencing larger weather extremes and so-called Arctic outbreaks that have delivered record-breaking cold and snow at lower latitudes around the Northern Hemisphere. Exactly what controls these patterns and what to expect going forward is an area of intense debate among researchers. For a while, the leading hypothesis was that the changes were tied to the sea ice cover changes. As the weather changes and sea ice cover changes appeared to be coherent. But as everybody knows, correlation is not causation. And a recent intensive modeling intercomparison project shows that the situation is more complicated and we need to pay a lot more attention to polar tropical connections higher in the stratosphere. Next slide, please. As things are changing in polar regions, biology is responding. One important theme is the migration of species. Starting with plants, the Arctic is clearly greening. Trees and shrubs are replacing lichens and grasses. Certain plants are blooming earlier. Insects are migrating northward. So all of these changes create winners and losers higher in the food chain. So for example, caribou who rely on the timing of nutrient-rich flowering plants to feed their newborns are not able to get the calories they need in traditional feeding grounds as the blooms have occurred earlier than they deliver their young. Muskox, on the other hand, are thriving as the snow retreats and makes it easier for them to get to their food sources. For indigenous peoples whose cultures and ways of life revolve around subsistence, these changes are strongly impacting their ways of life. Next slide, please. Species migrations are also taking place in our oceans, and the open water is causing changes in phytoplankton composition, which is at the base of the marine food chain. And that ripples up through fish and other marine food chain dependent species. For example, salmon are being caught in northern reaches, not previously known in oral history. In addition to the changing ice and warming waters, the oceans are subject to acidification as they absorb the excess carbon from the atmosphere. It turns out that this is also most pronounced in polar regions because colder seawater can absorb more CO2. Also, the surface of polar oceans tend to be relatively fresh and so less able to buffer the pH. This turns out to be important because life cycles of many organisms are finely tuned to ocean chemistry. Those that make their shells of calcium carbonate are challenged to do so robustly as the pH declines. Several such tiny pteropods, as shown here, are sometimes called sea butterflies or snails, are important components at the base of the food chain for fish. That matters because about 10% of the world's fish catch is from the Arctic. And over half of the US catch, constituting A more than $10 billion industry is from Alaskan subarctic waters. In Antarctica, as I mentioned, fishing is regulated by the Convention for the Conservation of Marine Living Resources. And economic studies show that this industry is about $100 million and growing. So all important reasons to gain a better understanding of what to expect as atmospheric CO2 rises and the polar oceans continue to absorb a disproportionate share of the burden. Next slide, please. Getting back to the issue of sea level rise, which I foreshadowed in my opening slide as a big kahuna, both the Arctic and the Antarctic turn out to be critical contributors. So in the photo on the left, you're looking at the surface of the Greenland ice sheet, which has been subject to ever more melting. And as water melts on the surface, it tends to flow and disappear vertically and photogenically down through drainage cracks known as moulins. On the right is a graph showing that sea level has been rising at an increasing rate. Sea level has risen and fallen by over 120 meters through glacial and interglacial cycles that occur on about 100,000 year time scale. The last glacial maximum was at about 22,000 years ago, and we saw sea levels 120 meters lower than today. As it rose, it stabilized, and for about the last 10,000 years was rising at about 1 millimeter per year. The current rise can be attributed to three main factors that are approximately equal in magnitude. One is that as seawater warms, it expands. Another is that small glaciers and snowfields around the globe are in decline. The third is that the world's great ice sheets in Greenland and Antarctica are on net losing ice to the sea. Okay, so let's talk a little bit more about land ice going into the future. The current global inventory of mountain glaciers hold the sea level rise equivalent of about 0.4 meters or a little over a foot. So even if we lose all of those, that would be the maximum amount of sea level rise. The future is really about the ice sheets. Greenland holds about 7 meters of sea level rise and Antarctica about 58 meters of potential sea level rise. So this is not to suggest we think there's an immediate danger of them disappearing. However, their rate of ice loss is accelerating. And there is a reason to focus in the near term on about 5 meters of the possible Antarctic contribution that I'll get to in a moment. So available data show that Greenland is losing about ice at about twice the rate as Antarctica at the moment. So if I can digress, when I was in graduate school, we had just begun to accumulate a satellite-based whole of Greenland perspective on ice loss. And the operative notion from the early record was that it was highly variable and there's no net trend. However, as the record accumulated, it became apparent that the trend had been masked at that time due to a global cooling associated with the 1991 eruption of Mount Pinatubo in the Philippines. Of course, there's a seasonal growth and loss cycle of the ice sheet, but now it's abundantly clear that we are losing ice on average and that the rate of loss is growing. Next slide, please. So as I mentioned, Antarctica is also losing mass about half as fast as Greenland at the moment. Science community, however, is really concerned in particular about that loss rate picking up. And here I'm going to tell you the two reasons for concern. As I said, Antarctica is like a sleeping bear. Although it constitutes 40% of the Southern Ocean constitutes 40% of the global oceans, it has absorbed 90% of the excess heat from the atmosphere. So the deeper levels of ocean are warmer, and as they interact with the floating ice shelves surrounding the Great Antarctic Ice Sheet, they are melting them. And as they're melting them, we are losing the ability to hold back the ice on the continent. This is particularly important on the West Antarctic ice sheet because what you're looking at on the right diagram is a picture of the bed elevation above sea level. And the bluer colors are areas where the current bed height is below sea level. As you can see, much of the West Antarctic sheet is below sea level. So what happens there is as the ice melts back, there is nothing to stop warm seawater from continuing to eat away at it. It's not as though it rises high enough to escape. So that is particularly concerning and could, in fact, cause the rate of sea level rise to dramatically increase. So there were a couple of papers just published in May in Nature magazine that gave a good sense of the state of research in this area. One paper pointed out that by a particular mechanism that had not previously been considered in models, that if we did not stick to the levels of warming agreed to in the Paris Accord, we would be likely to experience a dramatic increase in sea level rise. Another paper came to a conclusion that wasn't quite as dramatic. It's extremely important to know because by 2050, even a sea level rise of about a foot is going to push average annual coastal floods higher on land, now home to at least 300 million people. And high tides could permanently rise above land occupied by over 150 million, including 30 million in China. So without advanced coastal defense and planning, populations in these areas may face permanent flooding within 30 years. So there's plenty of more work to do to figure out in short order where we're headed. Next slide, please. Okay, so in the meanwhile, we're working on minimizing the environmental impact of our research, as illustrated here. The snowmobile, by the way, in the lower left is an all-electric vehicle that we sponsored a student engineering group to participate in a contest to create for us. And then in the middle, it may look weird to see tractors, but what we have learned is if we deliver our fuel to South Pole Station by aircraft, it's extremely energy inefficient. If we drive, dragging what you're looking at there are bladders of fuel with a tractor train, we can gain more than twice the energy efficiency. And so we've moved to every way we can think of to minimize our impact. And we also, as I mentioned in my very first slide, we're focusing on redressing inclusivity and attracting diverse talent needed to intensify the research base. So it's the only way we can hope to stay abreast of the changes and improve predictions and actionable translation of outcomes. Next slide. So that brings us to the end of my presentation. And now we have a chance to learn about your concerns and questions.
Thank you so much, Dr. Falkner. So everyone feel free to start putting some of your questions in the chat bar, and we'll field them here. We also, well, I think we've got enough people. I think that's the best way for us to manage it. If we have a smaller group, sometimes we can have you actually ask the question yourself. But yeah, what do you want to know about polar regions? People are quiet this morning.
I see one, let's see, point from Jim Kahan.
Yes.
So just to be clear, do we have the ability, I'm going to put my video back on. Maybe we can stop sharing this.
Yes.
So we can see people.
There's a...
I'm getting my gallery view up here so I can see as many people as possible.
We just received a question from Kellen Standley. Would you explain zombie fires more?
Yeah, so a lot of the tundra area is underlain by peat, which, you know, you may be familiar with. It's a very good form of fuel that's been used so in Ireland for centuries, for example. But what can happen is if this peat ignites and then gets covered by snow, it can stay smoldering under the snow cover. And when the snow cover disappears, reignite and continue to burn in a subsequent season. So that has happened on several occasions. So it's an unusual challenge with respect to fire that it'll keep going to that magnitude.
Lee DeCola asks, how do you balance the big sea footprint of Arctic research versus its value?
Excuse me, I'm sorry, can you repeat the question?
The big carbon footprint, big C was the way it was written. How do you balance the big carbon footprint of Arctic research versus its value?
How do I balance that? Well, it's a good question. And I would say we're in a transitional period of trying to minimize that footprint. And that is happening in many ways. We're now able to observe autonomously as opposed to have to invest all the energy it takes to either fly or send people by ships to remote field sites. So, I don't have the calculations for you. I can't answer that question in a numerical sense, but it is true for all of us and all we're doing right now that we have to reckon with how important it is to actually physically be moving people and things around and expending the fossil fuels to do so.
Jim Jackson asks, when did we first understand polar amplification of climate change?
We have known for decades from the earliest climate models that we would expect it. But those models weren't entirely aligned with what we were observing in terms of magnitudes and things. So we've been refining since the 80s our sense of how all of the factors interact, and we still are not there. We still don't have all the feedbacks appropriately captured. So as I mentioned, this is an active area of research.
Candace Lieber, class of 96, says, have the Alaskan villages that will be impacted started to plan for moving? Have they accepted that this is going to happen?
Yeah, that's an intensely emotional situation to have to move from your homes. So the answer is people recognize the need to move. The resources haven't necessarily been made available to all of the locations that need to undertake a move. So it's a mixed answer. And it's an expensive proposition. So really it's a work in progress. This, of course, as a basic research agency, we don't necessarily fund that directly, but we do like to take the research that we fund that shows, that permafrost is changing, that erosion is continuing and so forth, to let people be informed about making those decisions and in principle in advance enough so that they do it before it's a disaster. In Shishmaref, it happened a lot of the front of the villages that front the sea, infrastructure was destroyed before that the whole problem was fully reckoned with. But there are efforts underway by a number of agencies in the state of Alaska to try and address the problem. Haven't succeeded to get there yet.
Emma Rowe, class of 2006, asks, would you tell us the story you mentioned that you would tell if there was time?
Oh, yeah. I think I was saying I wanted to note the personal experience I had with sea ice at the North Pole. So while I was a professor at Oregon State, I worked with a project called the North Pole Environmental Observatory. I had colleagues at the University of Washington, Monterey, and around the world who would meet at the North Pole to try and take the pulse of what was going on in the ocean there and so forth. My component of the work involved flying to the sea ice surface in a number of locations to kind of do oceanography by airplane. So we use this wonderful airplane called Twin Otter. which doesn't require too much in the way of length of landing and takeoff. So we would fly over the ice cover, find a place we thought was sufficiently long to land, and the pilot would come down over it and, you know, fly close to the surface and touch the skis down, and then go back up in the air, come back and check to see whether there were any cracks or anything. And it used to be the case that the pilots who had some experience doing this could tell by just looking at the ice cover how thick the ice would be underneath, you know, and of course you can't land on ice that's too thin. But we did this for over a decade. In the last part of that time frame, because the ice was opening up and disappearing, it revealed a lot more open water, and then there was a lot more snow that got put on ice, and therefore the appearance of the snow no longer was well correlated with the thickness of the ice underneath. One of the last times that I went north, we landed on ice and we would jump out of the plane, we'd open up the cargo doors and we'd drill through it. And then we'd set up a gantry with a winch and put a shelter around it and lower our instruments down to catch water and measure properties in the ocean. When we drilled through the ice, in this particular case, the weight of the plane was depressing it so that normally there would be what we call freeboard. Before you see the water, you'd have some thickness of ice above it. And in this case, there was none. And the ice was quite thin, and they were paging through quickly to determine whether this was thick enough for us to stay. I think it was one of the hairiest moments that I've had in my experience in the North. So the bottom line was, I remember thinking when I first started doing work in the Arctic and going to the sea ice like this, my kids, grandkids are probably going to think their grandmother was a nut if they hear about what I do. I didn't expect to see it in my own lifetime. So that's what I wanted to share with you. It is happening fast, and it was, you know, shocking to all of us working there that it was happening quite as quickly as it is.
Margot Tollefson, class of 1973, asks, is anyone doing statistical modeling of warming?
Statistical modeling. People are doing all kinds of modeling of warming in all domains. So the answer is yes. We have a strong investment in a range of the types of modeling. We can often gain insights by exercising pretty simple models. As the models become more sophisticated and more knobs and buttons to turn, it can be more complicated to understand what you're getting out of them. But we are pushing forward in all domains. And actually, one area that's of interest right now is to use, as we do the more complicated modeling, use artificial intelligence to analyze those models and see what we're learning from them, and to run what we call model ensembles, because much like weather, as you start to predict the environment going forward, you know, there's an element of chaos. So, and much like whether you'd like to constrain and bring those models back to reality by actual observations, to the extent we can, we do that. But as we push ahead to predict further into the future, we want to run the models many, many, many times in order to get, you know, the average sense of where we're headed with things. So there's a lot going on in the modeling efforts these days.
Eugenie, I might not be saying that correctly, Lewis asks, what are ways we can foster greater diversity in training programs related to preparing for green careers? If you were to encourage young people to pursue studies related to climate, how would you recommend that they prepare?
Well, that's a great question. Kind of brings us back to this whole celebration of the environmental studies theme here. You know, in the day when I went to graduate school, the thought was, if you didn't have enough depth in a particular classical discipline, then you'd only be taking a superficial look at the nature of the problems. There's some truth that persists in that way. However, I think we were not good at training ourselves to work across disciplines to tackle these complex issues that inherently cross disciplines. So one extremely important thing we need to do is to be training the next generation to work in teams and to be able to talk across diverse areas. There are so many specialized languages that come along with the branches of science that cut, across the climate issues that it takes a lot of training to be able to understand and cross over. So I think my hope is that going to a place like Reed, where you're taught basic critical thinking skills, is very important, but also being able to work in a team fashion in that way is really important. I think Reed was responding to the fact that young people were seeing this as an important area back when it established the degree. Many colleges and universities across the nation were also answering to the interest. So, but I think, there are many pathways to contribute to this problem because it is so broad, including economics, including human behavior. How do you prepare for disasters? Well, human behavior is an important part of that. So how do you integrate that into preparations and so forth? So there's just so many dimensions. So I feel like the answer is that that people, like as always, should pursue their passions, but as people training people and preparing them for future careers, they need to keep these factors in mind.
Thank you. Mark McLean, class of 1970, says, one of the concerns about the Antarctic ice sheet is that glaciers are contained by terminal moraines below the sea level. As the bottoms of glaciers melt, the glaciers may float over these barriers, leading to massive glacial avalanches. How big a concern is this in the larger scheme of polar warming?
That is exactly what I was trying to illustrate with my little diagram. That was a side cut showing a floating ice shelf. And where the ice hit the ground is called the grounding line. And that is the concern. So it's a very strong concern. And in fact, so strong that it is, when we did a National Academy study asking what are the most important things we should be supporting for science in Antarctica right now, that emerged as the #1 thing. And that in particular, that we should focus in on what's called the Thwaites Glacier area of West Antarctica, because it's moving quickest right now. It's responsible for the bulk of the net input of ice to the ocean, and it is vulnerable in the sense that I'm just describing. So we embarked on I would call it like a Mars rover, all out study on the Thwaites Glacier system in partnership with the British Antarctic Survey and the national science funding agencies in the UK. And we're in the middle of that now. Unfortunately, we got about a year into getting going on it, and it was meant to be at least a 5-year program when COVID struck. So we kind of had to put things to the side. But that will be resuming, and that is in fact, going to be about a $25 million investment on our side, plus other international partners are contributing.
Jim Kahn asks, did the progress of your research program suffer during 2017 to 2020?
2017. So you're talking about the previous administration, I believe,
Yeah.
by choosing that time frame. I know why you're asking that, but the answer is we pushed out on the things we felt were important. Every year, the president's budget proposed significant cuts to NSF overall, and that would have affected us. But Congress came back, both sides of the aisle, and ended up appropriating more than the request to us as an agency. So we have pretty solid bipartisan support in Congress as an agency. So the answer to your question is, it didn't really slow our progress. The main thing that's hampered us recently has been COVID. And because you have to live in close proximity in these remote environments, and we're not set up with the sophisticated medical capabilities that we are stateside, we had to dial back our science dramatically. We had to reduce the number of people we were sending to Antarctica. We managed to figure out how to do everything we needed to, say, keep the lights on, so to speak, do the very minimal to keep things functioning, but we didn't do the science we had hoped to do during COVID. Unfortunately, we're looking at having to stay dialed back over the coming season because one of our major jumping off spots to go to Antarctica is through New Zealand. And while they did a remarkable job at preventing COVID from being a problem in New Zealand, they've been slow to march out on vaccination. They could afford to be slow. And we must quarantine our people there before they can be sent to Antarctica. And we were subject to their national restrictions in that regard. They have a strict 2-week quarantine period. So we will continue to be restricted in how many people we can move and how quickly we can move them to Antarctica over the coming season. Very hopeful with the vaccines and so forth going forward that that situation will change in the following years, but it's going to impact us this coming year. We're in the process right now of trying to judge what level of risk we're willing to take in other parts of the Arctic. Of course, we didn't want to be the source of COVID to the Arctic. The 1918 flu was devastating to Arctic communities. So that was in our minds as we were pushing out. So we also did a lot less science than we normally do in the Arctic. It's a bit different system. We're not solely responsible for all provision of all of the support in the Arctic. And so we're, in fact, have spent all week struggling to figure out exactly what risk level we're willing to take in order to allow our scientists to resume as much science as possible. Thank you for the question. I think you need to go on off mute, Amy.
Thank you. I was drinking my tea and didn't want everyone to have to hear that. Eugenie Lewis asks, you mentioned all hands on deck. What actions can ordinary citizens take to have the greatest impact on climate change at the current time?
Well, there are a number of things. You can exercise your voting rights. That would be a very important one. And, I mentioned 2 numbers about New York City versus Portland for water. And I did a little research on that too. So I'm pretty proud of Portland for its ability to conserve water. They made a concerted effort as a municipality to do so. It's very impressive. I think, that's what we're going to be needing to do is supporting efforts all over the country to preserve resources, to pay attention to those things that are stressing the planet and to contribute to being part of the solution. The exact pathway forward isn't entirely obvious, but, we don't have a lot of time to play around before we really jeopardize our future. So I think we're going to see a lot of changes that we should embrace. It's not easy to embrace them, but we definitely need to do so. I guess one of the biggest challenges, however, is, as we're being faced with such challenges, is generally the people that have this least potent voice that get hit the hardest. So that's another important thing to keep in mind, that as the people who are out there who are focusing on social justice and housing the homeless and everything else are also important contributors to solving the problem, because it really can't be all hands on deck if we have these marginalized groups. not easy problems. They're big problems to tackle, but these are the kinds of things I think Wheaties excel at.
John Hudson asks, class of 1952, what is the future of the glaciers on Mount Rainier and other mountains in the Pacific Northwest?
Well, that inventory of mountain glaciers would include those. We know they're retreating. They're retreating all over the globe. And that, when I said if you add them all together, the total volume of ice equates to 0.4 meters of sea level rise. So, you can readily find on the web information about retreat of specific glaciers if you're interested, but in general, that they are disappearing.
Jeff asks, how high will the ocean rise if everything melts? When I was young, the estimate was 300 feet. Since then, the estimates have decreased somewhat. What's the current estimate? Please discuss briefly.
Right, so I mentioned we got a half meter from those distributed mountain glaciers. We have about 7 meters from Greenland, and we have 58 meters from Antarctica. So you could add all of those up and multiply it by about 3 if you want to think in terms of feet, and that will give you a sense. So it's not hugely different from what you remember, but I don't think that you should consider Antarctica 58 meters to be even within the next few hundred years, but you should consider about 5 of that to be under more immediate threat. That's the bit that's in West Antarctica, held back by the ice at the moment that I discussed.
Switching gears, there's been an artist in residence program in Antarctica. Do you know anything about it? And this is from Pat Music.
Yeah, so we have an artist and writers program that has existed more or less since the inception of the US folks going to Antarctica. We formally established a funding program for it in the 70s, 80s. And we've had to put it on hiatus as we experienced COVID and some other pressures on our program. So it's being studied right now to figure out how to best support it going forward. There's some goofy things about how we support it. Congress has really mixed feelings about it. I've had to answer, since I've been in my role for nearly 9 years, almost every year, as to why I'm wasting taxpayer money on such a thing. And I come back and I say, well, we conduct a competitive process, and these artists and writers are selected in order to be able to transmit to the public in an accessible fashion the importance of the science that we do in Antarctica. And we only give them $1 when we award the grant. We do support them to travel to Antarctica and while they're there, but we otherwise provide no support. They have to rely on their networks of galleries or publishers or what have you to make sure that what they're doing gains public access. And generally when I give that answer, people are like, okay. And then I say, well, we even take the $1 away once we award the grant, but we needed $1 just because of the software. So I do believe it's extremely important. And I do believe we've done some really well received projects over the years in that way. However, when you have to submit a proposal as an artist or a writer, that's the same as a scientist has to submit, same format, and then be judged in the same way science would be judged, I don't think we necessarily get the best outcomes. So we're looking at, does it make sense for another entity to compete such a thing rather than us directly do it at NSF? But someone that we would sponsor that has really good networks into, the people that do distribute art and writing. So it's all underway right now. It is extremely important. There is a commitment to resume it. We're just studying exactly how to do it.
I have a question, Dr.
Sure.
Falkner. I'm curious about, I've read a lot about the opening up of shipping lanes in the Arctic with the melting of the polar ice caps. And there's obviously a lot of interest in that. There's a lot of people who want to make money off of that. And I was curious what you know about it and how you think it will affect communities in the Arctic, if that comes to pass.
Right. No, it's a great question. I mean, you can cut a significant length of time in shipping things across the top of the Arctic between Europe and Asia, for example. So it is of great interest. However, even though the sea ice is diminishing, it still exists. It still exists seasonally. It's likely to continue to exist seasonally, in part because winters are 100% dark, and you know, it does get cold enough for it to form. There is some danger in the fact that you have more open water. It's almost safer to go through fixed sea ice, although not easy. But with sea ice bobbing around in unconsolidated forms, it poses a threat to ships, and particularly if there are storms and so forth. So only well-equipped icebreakers are really safe in such a situation. Insurance companies recognize all this. They have not jumped into the fray to underwrite, you know, shipping in the Arctic. They recognize that there continues to be, you know, significant threats. So we have seen an increase in traffic. We've seen an increase, for example, in tourism prior to COVID, and I suspect it will resume because certain areas have been open that hadn't been open, like the Canadian archipelago, which is an amazingly beautiful, wonderful place and fantastic to experience. So I'm not surprised that tourists would like to go there, but couldn't navigate them even 2 decades ago. Now you can much more reliably. But you know, going high up into the Arctic or coming along the Northwest Passage, there will remain challenges. So people are preparing for it. We talk about it a lot. The US is particularly concerned that we have what we call domain awareness, that we have sufficiently well-provisioned US Coast Guard icebreakers to deal with anything that comes up in the way of problems affiliated with shipping, you know, assistance for people stuck in the ice, et cetera. At the moment, we don't have a robust Coast Guard fleet. Congress has appropriated money to replace one of our very capable breakers. We probably need more in order to do the job justice. So they started in on partially funding a second. I didn't get a chance to read the Coast Guard appropriation, a recent one, but they may have even in the president's budget asked for a third, I'm not sure. But it is still limited when you look at the vast areas they would have to cover. So there's also inadequate infrastructure to handle, there's no ports in the high Arctic, in the US high Arctic. So there's a lot that would need to be done to support increased shipping in a sensible way. An interesting sort of sidelight is that we have research vessels go to the area, and the research vessels that do from the US consult the local communities because there's a subsistence whaling tradition, and the subsistence hunters would use the ice. They'd go out on the ice and then launch small boats to get to the whales. And there had been concern that passage of science ships were cutting the ice that they would use for transportation and were affecting the migration patterns of the whales. So we had established years ago the need for scientists to try and deconflict this kind of thing. It remains an issue, of course, for Indigenous peoples going forward, how they can benefit from increased shipping in the area and how they can avoid the problems affiliated with it.
Thank you. Olga, did you have a question? Let's see. Speaking from opening up travel and tourism, I know you hosted a group of alumni to Antarctica in the past. Thank you for doing that. And maybe we'll be able to repeat that trip at some time in the next few years. I was just wondering about your thoughts on that.
Well, I'm certainly willing to consider that. I do want to tell everybody, I've been at my job that I described to you. It will be 9 years come August 1st, and I have recently given notice that I'll be stepping aside from it. I will be detailed to the State Department to work with their Office of Science and Technology Cooperation for a bit. But I think, following that, I would be game to consider doing another trip. It was a fantastic experience. I do think the industry will recover. They were hard hit. They went from nearly 75,000 people went down to Antarctica on ships. And then in COVID, they were down to a dozen or so, which is a dramatic change. But there were new ships being constructed to support the growing interest there. So I do suspect that will continue. What I like about the organization that oversees all those ships, it's called the IATO, the Antarctic Association of Tour Operators, International Antarctic Association of Tour Operators. They actually require all of their activities to be done in accord with the terms of the environmental protection pieces of the Antarctic Treaty, and they really include a lot of education. So the people who go to Antarctica come away as ambassadors for the Antarctic, and we need that. I mean, the numbers are still very small compared to the global population, but for the people that go and learn about it and can come back and share with their friends and neighbors and communities, that's a really favorable thing. So.
We have a comment/question from Kellen Stanley. Given that from a scientific perspective, we already know basically what we need to do, it seems that the rate limiting step is understanding in the general population. I think it would be helpful to allow people to have a more direct experience with the physics of gases. To this end, I think it would be instructive to make a thermos for tea or coffee filled with heat trapping and non-insulating gases that people could experience the difference in insulation capacity phenomenologically by experiencing how quickly their tea or coffee loses heat over the course of the day. I would think NO, CO2, and O2 might be a good range for comparison. Do you think it could be an interesting or useful way of informing the public?
I think those kinds of things are terrific ways to inform the public. I haven't done that particular one, but another one that I really like to do that's on the same vein is people often get confused about, they think if, the Arctic sea ice is melting, sea level is going to rise. Well, that's not true. The sea ice is already floating, and as it melts, it's not going to cause the sea level to rise. The melt of ice on land that goes into the sea will cause it to rise. So I like to illustrate that by having people do a simple experiment where, and they think about it, they have a glass of water and an ice cube. So and when you start with the ice cube floating in the water, that's sea ice, you mark the level, you let it melt, and you see what happens to the level. Okay, and then you can also do the same thing where you have just the water, mark the level, and you say, okay, now ice is coming in from the land, and drop it in and see what happens to the level. It's most fun if you do this and if you enjoy alcoholic beverages, to do it with something like that. It takes a little while. I've done it with little kids, showing them, and as we were talking about other things, we then come back to the glass. Almost everybody predicts that if you put an ice cube in the water and let it melt, that the level is going to go up. And so it's a little counterintuitive. I don't know why people think that way, but that's generally their thought. So it's very illustrative. So what you're talking about could be as well. You'd have to play around and make sure you get it just right so that the effects are obvious to the uninitiated. But those are great ideas. Those are great things you can do in communities and at fairs or what have you. So I thank you for that suggestion.
Mark McLean, class of 1970, says, there has been some discussion of competition for oil under the Arctic seafloor. Is this an immediate concern, and what issues does it raise?
Absolutely, it's an immediate concern. It's estimated that there's about 30 billion barrels of oil in the Arctic, and there's much, much more in the way of natural gas reserves that are tappable. And, there has been sales of offshore leases to explore for that in the, for example, Alaskan Arctic, and a lot of it is known to be there. And then various companies have invested a huge amount of money to try and go explore for those options. For example, Shell was up there in full force. They had a bunch of snafus as they were trying to do that and decided to pull out altogether. But I don't think in the long run, it's going to completely diminish the pressure to look there. I don't know if any of you have been able to go see the Alaskan pipeline, but that's one interesting thing. And from an engineering standpoint, that pipeline was designed to deliver fuel from the North Slope down through Alaska. It has to be up off of the land because that fuel is warm as it comes out of the ground. And you would just melt the pipe into the tundra. So it's got some specialized footings that keep it off of the land. And it goes a very long way. It was also designed to have a certain quantity of fuel flowing through it. And as we've used up what's been there for reserves, the pipes are less full. The less full pipes, as the fuel moves through it, then glubs as it goes over hillsides and creates vibrations that are affecting those footings, the stability of those footings. And it's a whole complicated thing. So there's some people who are like, if we could just get a little bit more oil in them, then we could prevent all of this damage to the infrastructure. And of course, make the money on the side or whatever you want to say about how you feel about that. But there are a lot of pressures there because of things like that. Moreover, it's interesting too, because when I visited what they call pump station number 1, right up on the North Slope in maybe 5 or 6 years ago. And they, in order to keep the fuel flowing, which has some natural paraffins, wax kinds of substances built up in on the pipeline, they send down what they call a pig, kind of look like a big bullet, that goes down and cleans out the pipe. So again, as the temperature of the reserves that they're tapping has dropped over time, they've gotten more buildup, and that's another complication. So, it's interesting. There are a lot of issues associated with it. But in terms of thinking of the region as a resource, it's not only oil and gas, so that's a very important driver. In fact, there's active oil and gas exploitation in the Norwegian Arctic, of course, that has fueled their amazing economic boom. But there are other things. There are minerals. We're very concerned about our ability to get our hands on some of the critical minerals in a future economy that's reliant on a lot of, for example, rare earth elements in our phones and everything else. So there's a lot of interest in Greenland and Canada, and even the US Arctic to go after those minerals to mine in the Arctic. And there is mining that does go on in the Arctic. So those are important resources. And I think fishing needs to be put into the resource realm as well. So the Arctic is under a lot of attention due to the potential for resource extraction in our changing world. So I thank you for that question, because I didn't mention that in my talk.
So this is going to be our last question from John Hudson, class of 1952. As the land ice melts, the land rises. How does this affect the rising sea?
Right, that's important. So one thing I didn't mention, I kind of talk about sea level as though it rose uniformly everywhere on the planet, which it does not do. There are many factors that figure into how exactly sea level rise manifests itself on the planet. One important factor is how the ocean circulates, and that can affect how water piles up in basins and where you're going to see the bigger changes. Another factor is, as was noted, as really heavy masses on the land, such as ice, melt and go away, the land rebounds. We call this isostatic rebound. And there's a couple of time scales affiliated with rebound that affect how quickly the land does recover from having been depressed by such weight. So the bottom line is that sea level rise is going to be a very regional, heterogeneous phenomena. So one of the things researchers are trying to do right now is to put all those factors together to get as accurate a rise rate as possible. And I do want to point out one thing that I've found fascinating that may be a little counterintuitive. Right now, if you think about it and you were to think about it simple-mindedly, you'd say, well, if Antarctica melts, entirely, then you might think that that sea level would rise around the region. In fact, the mass, or gravity pull on the ocean from the mass of ice, it will be gone. And so in fact, as Antarctica melts, sea level isn't going to rise locally from that per se, it'll actually rise elsewhere on the planet. So, and that also has its own time scale of change. So I thank you for asking that question. It is something that we are investing a lot of time and energy in trying to be sure that we understand at a regional level, which is what is needed to do actionable outcomes in terms of preparing for it.
Well, thank you all. Thank you so much, Dr. Falkner, for sharing your stories and expertise about polar regions and climate change. And yeah, you all had some wonderful questions, and I think this has been a fantastic discussion. I've learned a lot. So that's the end of this session. In about 30 minutes at 11 a.m. Pacific, Ben Rankin, class of 1987, and Ron Shiget